All right, I want you to imagine something for a second. You're standing in your school's chemistry lab,
Okay, I'm there.
and on the workbench, right in front of you, there are two glass beakers.
Mm-hmm.
Both of them contain these clear, colorless liquids. I mean, they look absolutely identical.
So to the naked eye, they're basically lookalikes. You can't tell them apart just by looking.
Exactly. Lookalikes. And you know for a fact that both of them have an OH group, a hydroxyl group, inside them.
Right.
But then you take a dropper of phenolphthalein indicator. You add just one drop to the first beaker,
And
and nothing happens. Stays colorless, just looks like water. But then you add that same drop to the second beaker, and poof, it turns pink. Immediately.
that is a classic lab moment, the magic trick of chemistry.
But here's the thing that gets me. If they both have the exact same AOH group, why did one act like an acid and turn pink while the other one just sat there?
That question right there, that is the key question. And honestly, it's the core mystery of Unit 7, alcohols and phenols.
I knew there was a catch. It's never as simple as it looks, is it?
In organic chemistry, there is always a catch. So today we're doing a deep dive into this, this sibling rivalry between alcohols and phenols.
Sibling rivalry, I like that.
And we are looking strictly at how these two families differ, which, as you know, is a massive part of the CBSE Class 12 chemistry syllabus.
And before anyone thinks, oh, great, another lecture, tell us why this actually matters. Beyond just the board exam, why do we need to know this?
We care because understanding this difference lets you predict what will happen in a reaction. See, if you don't get this, you won't understand why one substance alcohol can be oxidized to make fuel or, vinegar for your food,
Right.
while the other one, phenol, is used to disinfect hospital floors or make heavy-duty plastics, but it absolutely refuses to be easily oxidized.
So it's the difference between salad dressing and floor cleaner.
Precisely. And if you mix them up in an exam or in a real lab, the results can be, pretty disastrous.
Okay, that definitely raises the stakes. So let's get into it. We have alcohols and we have phenols. For a student listening, give me the zero-level explanation. What is the absolute simplest difference?
At the simplest level, it is all about location, location, location. It's about where that oxygen sits.
Okay, so walk me through the locations.
In an alcohol, the SOH group is attached to a saturated carbon.
Saturated carbon meaning?
A simple, single-bonded carbon atom. Just think of a standard carbon chain. It's simple, it's flexible.
Got it. A generic building block.
Right. But in a phenol, that same OH group is attached directly to a benzene ring.
And that's it, just what it's attached to.
That is the one fundamental difference that changes everything.
Okay, but I have to ask, how does just being on a ring change it so much? I mean, oxygen is oxygen, isn't it? Why does it get a whole new personality?
That's a very fair question. It's not just the attachment, it's the environment. I saw this great analogy in our notes about a wild animal. Can we use that? I think it explains the behavior perfectly. Oh, I love that one. It's brilliant for visualization. Yes, let's do the wild animal analogy.
So imagine the H group is a wild animal,
Mm-hmm.
maybe a tiger, something energetic. It has electrons, it wants to react.
Right. A wild, energetic little thing.
In an alcohol, this animal is sitting on a saturated carbon. Think of that like a normal, quiet, open field. So the animal is young, energetic, curious, and very easily provoked.
So it's restless because it's just on this plain carbon chain.
Exactly. It wants to react. It's easily oxidized. It's like a puppy that runs around getting into trouble. You throw a reaction at it, goes, sure, let's do it.
But then you take that same animal, the HOH, and you put it on a benzene ring. That's phenol.
And this is where the magic happens. The benzene ring isn't just a shape, it's a stability machine. It tames the wild animal. The ring pulls on that oxygen, calms it down. So in phenol, the animal becomes defensive. It becomes acidic. It's stabilized by the ring's energy.
So the ring basically disciplines the HOH group. You could say that. The ring says, hey, calm down, share your electrons with me. And that changes the whole molecule's behavior.
I love that image. The alcohol is the hyper puppy, and the phenol is the disciplined guard dog.
That is a perfect way to put it. Now, if we can get technical for a moment, just to cover the why for the exam, what's really happening at the particle level?
Yeah, let's do the science. Because writing guard dog probably won't get me full marks on a reasoning question.
Probably not. So in an alcohol, the carbon atom holding the oxygen is spa hybridized.
Okay, pause right there. SPO hybridized. That's one of those terms students memorize but don't always feel. What does it actually mean for the bond?
Great question. Think of SPA as standard single bonds. It means the bond is long, it's a bit polar, and critically, it can break. It's just a single handshake between the atoms.
It's easy to break up.
Very. If a stronger partner comes along, that bond just pops off. That's why alcohols do so many substitution reactions.
Okay, Sput equals a single handshake. Easy to break.
Got it. But in phenol, the carbon is sposahybridized because it is part of that benzene ring. And here's the keyword you must know. Resonance.
Resonance. The movement of electrons around the ring.
Correct. The ring pulls electrons from the oxygen, giving the carbon-oxygen bond a partial double bond character.
Partial double bond character. That sounds much stronger.
It is. It's like using super glue. Instead of a single handshake, you're holding on with two hands. You cannot just break it off easily.
Which explains why phenols don't do the same substitution reactions.
Exactly.
So if I had to write down one anchor definition for my exam, something safe that works every time, what should it be?
Here is your exam safe line. You write, alcohols act as neutral compounds where the echo-H is on a saturated carbon. Phenols act as acidic compounds where the echo-H is bonded directly to a benzene ring.
Simple. Neutral versus acidic. Saturated versus benzene ring.
And please, I have to mention the biggest mistake students make.
Yes, the common error. What is it?
Students see the OH in both and they think, oh, OH group. They must do the same things. Never, ever do that.
It's a trap.
A massive trap. The context, saturated versus aromatic, makes their chemistry almost opposite. It's like confusing a house cat with a lion just because they both have whiskers.
Right. One purrs, the other might eat you. Context is everything. Okay, let's stick with analogies. There's another one here, the social context analogy. I think this one really helps with the acidity part.
Yes. This one is great for understanding the personality of the molecules.
So an alcohol is like a normal person, a regular person, easy to talk to, openly reactive. Life experiences like oxidation change them easily.
Right. A normal person reacts to things. You add an oxidizer to an alcohol, it changes into an aldehyde or an acid. It's flexible.
Now, compare that to phenol. Phenol is like a member of a noble family.
And the noble family is the benzene ring.
Exactly. The family status, that resonance, stabilizes them. You can't just push them around. They resist oxidation.
But, and here's the key to the acidity, because they're part of this noble family, they're more willing to donate.
Donate what?
A proton. A hydrogen ion. Think of it like a noble family donating to a cause. They can do it because the family structure supports them after the donation.
That is brilliant. So the normal person, the alcohol, is reactive but neutral. They don't give away their protons easily. The noble person, phenol, is stable but willing to donate a proton, which makes them acidic.
Yes. In chemical terms, the benzene ring, the family absorbs the negative charge left behind. That's why phenol is okay with being acidic. And alcohol has no support system like that.
This really explains why the concept exists, doesn't it? It's not just some abstract rule.
Not at all. It solves the problem of prediction. Without this, we couldn't explain why fermentation makes ethanol, which is safe in moderation, instead of phenol, which is toxic.
Right. Imagine if it made phenol instead.
A very dangerous drink. Also, we couldn't design drugs like aspirin. Aspirin has a phenolic group. Scientists had to know the ring makes the oxygen behave differently to make it correctly.
It really is the difference between medicine and poison sometimes. Okay, let's try to build a mental movie for everyone listening.
Let's do it. If you can, just close your eyes for a second.
Imagine a split screen. On the left side is alcohol. Picture a carbon sphere with 4 arms, that tetrahedral shape. One arm holds a pale blue OH group.
And see that blue OH group sort of oscillating, wiggling freely. It's not tied down.
Let's label that side, reactive, neutral.
Now look at the right side of your screen. This is phenol. Picture a hexagon, the benzene ring, and imagine it's glowing with a deep purple light.
Purple light. Very noble.
Very. The HOH is on a corner. But look closely, you can see arrows of light, the electrons, circulating from the ring onto the oxygen. The OH isn't wiggling around, it's locked in. It's part of that purple glow.
And we label this side, acidic, stable.
If you can remember that picture, the wobbly blue energy versus the stable purple glow, you can answer half the questions on this topic.
I can literally see it. That helps so much.
Yeah.
Okay, let's bring this back to the lab. We started with the phenolphthalein test.
Yeah.
Let's explain exactly what happened there.
Right. So phenol turns the indicator pink because it is wintly acidic. Its pKa is around 10.
A pK of 10. And a lower pKa means a stronger acid, right?
Correct. It's not a super strong acid, but it's acidic enough to donate a proton to a base. That donation changes the pH, and the phenolphthalein turns pink.
And the ethanol?
Ethanol is neutral. Its pK is way up at 16, which is basically like water. It holds on to its proton, so the pH doesn't change, and the indicator stays colorless.
So that color change is visible proof of the ring's influence.
It is. It's the molecular personality showing up in the real world.
Is there a technology or product that relies on this difference?
Oh, absolutely. You've seen those old, hard plastic electrical switches, or the handles on cooking pans that don't melt.
Yeah, that black, hard plastic stuff.
That is often Bakelite. It's one of the first synthetic plastics, and it's made from,
Let me guess, phenol.
phenol and formaldehyde. And you can only make Bakelite because phenol's acidity activates the ring to undergo a specific reaction.
And you couldn't use ethanol instead.
Nope. Ethanol is neutral. It doesn't have that activated ring. So no phenol, no Bakelite switches. That's a great exam point.
Okay, good to know. Now for a counterintuitive question.
Go for it.
Okay, so both have LH. We learned about nucleophilic substitution, swapping the HOH for something else, like a chlorine atom.
A standard reaction, yes.
So my naive assumption is they should both do it right.
That is a very logical assumption, and it's completely wrong.
I knew it.
Alcohols love substitution. It's easy. But phenol, it generally refuses to do this reaction at the carbon-oxygen bond.
Why? Is it that partial double bond character again?
Exactly. It's that superglue. The CO bond is too strong to just snap off like it is in an alcohol.
So alcohols do substitution. Phenols generally do not, at least not there.
Correct. Phenols prefer to react on the ring itself, but they protect that oxygen connection fiercely.
Okay, we're nearing the end. I want to get the cheat codes for the board exam.
The clarity lines.
Yes. Give me the simple sentences to write for full marks. Clarity line 1.
Phenols are acidic, alcohols are neutral.
And the why, the tieback.
You must add, this is due to the resonance stabilization of the phenoxide ion in phenols. Mentioning resonance stabilization is key.
Got it. Resonance stabilization. Okay, clarity line 2 on oxidation.
Primary alcohols oxidize to aldehydes. Phenols resist oxidation.
And the reason for that is?
Phenols don't have the right hydrogen arrangement, plus the ring stabilizes them. For your exam, just remember, alcohols oxidize, phenols resist.
Perfect. And clarity line 3 on substitution.
Phenols undergo electrophilic aromatic substitution. Alcohols undergo nucleophilic substitution.
Can you break that down one last time?
It's about where the reaction happens. For phenols, the reaction is on the ring, the hexagon. For alcohols, the reaction happens at the carbon holding the AOA.
Ring versus carbon. That's the ultimate distinction.
It is.
This has been so helpful. Let's do a quick summary for everyone to lock it in.
Let's do it.
Bullet point 1, the core idea.
Alcohol means saturated carbon, and it's neutral. Phenol means benzene ring, and it's acidic.
Bullet point 2, the mental image.
Blue oscillating energy for alcohol, the playful puppy. Purple circulating resonance for phenol, the disciplined guard dog.
Bullet point 3, real-world proof.
Phenol turns indicator pink and helps make Bakelite. Ethanol stays colorless and can't make that plastic.
And the final key rule to remember.
Aromatic makes it acidic. Saturation makes it neutral.
If you remember nothing else, remember that.
It will save you a lot of confusion.
Before we sign off, we always like to leave you with a little something to think about, a provocative thought.
Yes. So we spent all this time talking about how the ring changes the SOH group. But now ask yourself this. How does the SOH change the ring?
Ooh, flipping the script.
Exactly. Does that oxygen make the benzene ring itself more reactive to other things or less reactive?
That sounds like a teaser for the next part of the chapter on orthopara-directing groups.
It absolutely is. Go look that up. It connects all the dots.
Well, that is all the time we have for this deep dive into Unit 7. To all the Class 12 students out there, keep calm, visualize that purple glow, and you will nail this topic.
You've got this. Understanding the concept is 90% of the battle.
Thanks for listening. We'll catch you in the next deep dive.
Goodbye and happy studying.